Hi, I'm Nigasan Ragunathan, and welcome to my presentation on generating coordinated random traffic in UVM. I'm a master's graduate from the University of Washington in EE and an undergraduate of the University of Waterloo. And I currently work for Microsoft on the Silicon team in Redmond, Washington, where we work on a variety of different products which contain custom silicon. Okay, let's get started. We'll begin with an introduction and some background on the problem at hand. Then we'll dive into the proposed solution, look at how this would work with a sequence and a sample design, and finally, we'll look at how scalable the proposed method is. We all know that constrained random stimulus has many advantages over direct stimulus, allowing test benches to hit corner cases that don't fit the typical use case. Developing constraint random stimulus is usually straightforward for designs, but there are some complex designs where constraint random stimulus may be difficult enough to develop that directed stimulus would be the logical alternative. The inspiration for developing a method to coordinate random traffic came from a problem that we faced when we were trying to plan for our test bench. While we were planning, we repeatedly ran into scenarios where it would be difficult to have a sequence generate random traffic independently because this would easily result in illegal traffic being sent to the DOT. We were adamant about using random stimulus to harness its advantages and wanted to reduce the number of directed cases as much as possible. One of the reasons why constraint random stimulus would be difficult to develop would be the need to coordinate traffic from multiple sources, which is what this presentation will focus on. As you will see in the next few slides, by introducing a traffic manager, we were able to overcome this challenge, and it was possible to coordinate traffic generation across multiple sequences. Developing constraint random stimulus is usually straightforward for designs like this one, which consist of a single pipe where there is one primary input interface up top in blue and one primary output interface at the bottom in green, a register or control interface, and some miscellaneous sideband signals in yellow over here. Generating stimulus for this standard test bench is straightforward because the input stimulus has no dependencies, such as the current state of the design, and it does not have to take into consideration other data inputs. Unlike the simple test bench, this presentation will focus on this more complex DUT. In this more complex DUT, we have multiple data inputs, the three inputs at the top here. And all the data inputs must produce legal stimulus based on the current state of the design, which can be changed by stimulus from any other primary data inputs. Therefore, this DUT requires that the input stimulus is dependent on all the past traffic received by the DUT. Stepping back, when an IP has multiple input interfaces requiring complex stimulus patterns, which are mutually dependent on each other, it is logical to assume that the constraint random testing would take too much effort and maintenance to effectively develop and test in the traditional sense. Regardless, attempting the traditional method of constraint random stimulus would result in producing illegal traffic to the DUT, since subsequent traffic has to be dependent on the prior traffic to be considered legal input. This can't be handled through the normal sequence items and sequences, therefore directed stimulus would be more valuable in the short run. On the other hand, limiting the test bench to directed stimulus will result in fewer unique conditions getting produced. This causes a reduction in the coverage space of the traffic, leading to a much higher chance that a bug will be missed. The other alternative is to use a model to generate legal traffic, but this is essentially no different from using directed tests and holds the same disadvantages. In summary, it is clear that directed stimulus would ensure legal traffic to be produced, and there wouldn't be any concern with timing the different inputs so that they play nice with the other inputs. but this limits the test bench's ability to hit odd corner cases that are easier to reach with constraint random stimulus. This is where our proposed method of using a traffic manager comes in. What is a traffic manager? At its base, the traffic manager is a UVM object, which acts as a database to store any information that needs to be available to all the constraints for randomization, such as all the past transactions sent over each interface. This means that all the sequences will have access to this single shared traffic manager. Since it will be available to all these sequences, it can also store control knob values or any other information that needs to be shared across sequences. It is necessary to separate the traffic manager from what the test bench observes through the monitors due to timing constraints. The monitors only observe transactions after they have already occurred, whereas sequences need to know what stimulus is already generated and in flight before producing more traffic to queue up and be sent next. All of this is done to ensure that no illegal traffic is generated before a monitor has time to see it, as this can take several cycles depending on the protocol of that interface. Since the traffic manager is a standalone UVM object used in conjunction with a sequence, it is easily integrated into higher level test benches for vertical reuse in subsystem and SoC level test benches. One thing to note is that the name traffic manager sounds like it produces traffic, but it does not. The traffic manager is used to manage the information developed by past traffic, so it's easily accessible to all sequences. You might wonder, how is the traffic manager different from a virtual sequence? For a simple design, the traffic manager could be analogous to a virtual sequence, as it would coordinate traffic. In the complex design, where the sequence items are dependent on each other, all the information represented in the sequence items need to be gathered by the virtual sequence for each sequence item. Whereas the traffic manager, with the traffic manager, the sequences would do all the work of gathering the information instead. Once this data is gathered by the virtual sequence, each sequence would need to be aware of this information when generating the next sequence item. The traffic manager facilitates this data sharing so that each unique sequence on an interface can generate a new sequence item while being aware of all the dependencies across any and all interfaces. Typically, a virtual sequence or a sequence library sets up a sequence, starts the sequence, then gathers response data. By introducing the traffic manager, the virtual sequence doesn't have to think about setup or response data for each sequence, especially when there are so many sequences, as the sequences can essentially talk to each other through the traffic manager instead. The key point is that the traffic manager enables a decentralized approach to stimulus. I also get questions about how the traffic manager interacts with a virtual sequencer. And in short, the traffic manager is not aware or concerned with how the virtual sequencers and sequencers are connected to each other. The traffic manager coordinates dependencies, not stimulus arbitration. By using the traffic manager, the test bench can take advantage of a few of its benefits. The biggest benefit of the traffic manager is the ability to model complex design behavior for stimulus. This also allows for constrained random tests to be created through sequences which can handle complex stimulus rather than a large number of directed tests. This relieves the test writer of having to write many directed tests and unlocks the benefits of random testing where random testing would otherwise not be possible. The traffic manager also supports reusability, allowing higher level test benches to leverage the benefits of randomized testing as well. This figure demonstrates how the traffic manager would interact with the sequence's body. The sequence would use the traffic manager to check sequence control knobs to determine which set of constraints should be used. So that's this first pink box requesting data from the traffic manager. When it uses data stored in the traffic manager from past randomized sequence items to randomize a new legal sequence item, so that's this next box, this pink box where it requests more data from the traffic manager. And then once all of this is done, a new legal sequence item has been created. The new sequence item would be updated in the traffic manager with any relevant data from that sequence item. So that's where we have information going back to the traffic manager and it gathers anything it needs to get from a sequence item. And lastly, the sequence item is sent out and then the process is repeated. Here's an example designed to demonstrate how the traffic manager would be used. For this example, the DUT performs arithmetic operations such as add, subtract, multiply, and divide. There are three inputs to the DUT. So we've got our opcode and two operands, operand 0 and operand 1. The output of the DUT is the resulting value of the arithmetic operation. For this example, some requirements will be imposed on this design to illustrate the benefits of the traffic manager. So the opcode cannot be sent until the operands are received. And this means that the DUT expects the operand interfaces to be driven before the opcode interface. The multiply operations do not require two new operands and will execute using the previously loaded operands. So this means that the previous requirement only applies to add, subtract, and divide. The multiply is exempt from this operation, from this requirement. And lastly, multiply can only be issued following an add operation, whereas other operations have no such dependency on previous operations. So a sequence of opcodes like add, multiply, subtract would be legal, but add, subtract, multiply would be illegal since the multiply follows a subtract operation. Next, we'll look at what the traffic manager for this example DUT would look like. This traffic manager will store all the previous opcodes sent to the DUT in the previous opcode queue. So that's over here at line 5. This way, the sequences which use the traffic manager can restrict the multiply operations based on past stimulus using the previous opcode field. Our traffic manager also has a data loaded field on line 7. And this will indicate whether the operands have already been sent over the operand interfaces so that all the sequences are aware of whether new operands have been loaded or not loaded. And finally, our traffic manager will have a semaphore with one key to limit access to the traffic manager to one sequence at a time. Since multiple sequences are accessing the same instance of the traffic manager object, care must be taken to avoid using stale information. This can occur if two or more sequences were attempting to update the class members of the traffic manager simultaneously. To prevent sequence update collisions, an access semaphore with one key is instanced in the traffic manager. And this one semaphore is shared by the sequences through the traffic manager. Each sequence that shares the traffic manager is then responsible for obtaining the key before accessing the traffic manager's contents and returning the key once this is complete. This controlled access guarantees that only one sequence has access to the traffic manager at any given time and preserves the fidelity of the database. In this case, it makes sense to have only one key for the access semaphore, but there may be cases where more are appropriate. It's easiest to call the new on the semaphore in the traffic manager's new function, but doing this in the sequence would also be appropriate, as it's done in line 14. Moving on to the structure of a sequence, let's take a look at an example sequence's body. This follows the high-level flow diagram of a sequence shown a few slides ago on slide 9. The sequence starts by getting access to the traffic manager, which is on line 3, where we get the semaphore, access to the semaphore. Then it randomizes the sequence item using the information contained within the traffic manager. So this starts on line 5 here. Recall that one of the requirements is that multiply operations are unique and can only be sent following an add operation without loading new data operands. To apply this requirement, the operand sequences would access the traffic manager's previous opcode queue and observe if the previous operation was an add, as it's done up here on line 6. If an add was just sent, then and only then is it legal to send a multiply operation. Next, on line 13, since each opcode must wait for the data operands to be loaded, the sequence would have access to the traffic manager's data loaded signal to detect and wait for each operand sequence to report that the data has been loaded before the new opcode is sent to the driver. Since multiply operations are unique and don't require new operands to be sent, the sequence can bypass the waiting on the data loaded indicator if the next operation is a multiply. Once all the randomization is complete, the traffic manager can be updated with the information from the new sequence item, as it's done on line 17. We won't go into the update traffic manager's function, but this is basically where the traffic manager gathers all the data it needs from the sequence item. And then once that's done, the data loaded field can be reset, indicating that the loaded data has been consumed. So that's what's done on line 19. Once this is all complete, the sequence releases access to the traffic manager to allow another sequence to get access to it. And that's what we do on line 21. One thing that I overlooked when I created this example is that the traffic manager access should be released, then requested again before and after the wait for the operands to be loaded. So that would be between lines 13 and 14, access should be released, and then between 14 and 15, access should be requested again. The idea behind the placement of the semaphore requests and release is that a sequence should never hold access to the traffic manager for more than a delta cycle of simulation time. Because if it does, then other sequences are prevented from utilizing the traffic manager. The traffic manager and the sequences developed alongside the traffic manager are inherently portable and scalable for reuse in higher level test benches. Without the traffic manager, the directed tests used in higher level test benches would be more simple than the directed tests used at the block level. But with the traffic manager, the higher level test benches can leverage the complex stimulus for all test benches. That's the primary benefit of using the traffic manager at higher level test benches. There are many different possible configurations that the traffic manager can be used for. In this scalability example, there are 2 instances of the DUT with the inputs of each DUT connected to a common fabric. So we have DUT0 and we have DUT1 and our common fabric connecting those in black. The inputs on the fabric in this example are similar to the block level test bench, but it could have more inputs connected to the fabric. So we're going to use the same inputs, opcode, and 2 operands. Transactions are supplied on the master input interfaces and target either DUT0 or DUT1 as its destination. Each DUT has an output similar to the block level example. In this test bench, although no changes are needed to be made to the traffic manager or the sequence, each instance of the DUT must have a separate traffic manager instance to track the information or state of each DUT. So we don't want any information between the two traffic managers of each instance being shared. Since the sequences are connected to a fabric, each sequence will also need to select a target DUT. And this is how those new requirements would be implemented in the higher level test bench. In the test case itself, an array of traffic managers need to be created in the build phase, shown starting at line 5. So there would be one for each instance. Then in the run phase, each sequence is paired with an instance of the DUT through the traffic manager. And this is shown starting at line 17. This pairing can be changed later in the test or in different tests to further add complexity to a test. So here's an example of how you can do that. Here you can see a more complex test case where each sequence is randomly assigned to a traffic manager. So we just randomly select one of the traffic managers and a sequence is assigned to each. Each traffic manager contains the information necessary for a sequence to correctly generate a sequence item directed at the DUT instance belonging to that traffic manager. This is one example of how to pair sequences to a traffic manager, but the randomization can be done once or multiple times throughout a test. It can be limited to maybe one traffic manager or multiple traffic managers. The point is that there's flexibility with how a test can be set up. I want to end by summing up that using the traffic manager to coordinate stimulus generation builds on constrained random stimulus by adding intelligent randomization into the sequence. In cases where directed testing would be the only way to test the DUT, the traffic manager unlocks the benefits of constrained random testing. The concept of a traffic manager was successfully used at Microsoft for a real-world design, and it allowed us to stress the DUT through typical random tests so that directed tests were only used for the very basic test bench bring-up. One of the biggest benefits of using the traffic manager for our test bench was that coverage holes were quickly identified before coverage analysis, since we were not limited to directed tests. During the planning phase, we believed a significant number of directed tests would be required to achieve our coverage goals. But since we did not have a comparable DUT with directed tests, we were unable to compare and quantify the verification savings there. However, we did find that when we analyzed block level functional coverage, the initial numbers we saw there were higher than the numbers for the same functional coverage of a subsystem level block, which required more directed tests. Thank you for listening to this presentation on generating coordinated random traffic in UVM.